Alright, in this video we're going to look at the first couple of examples from the derivatives lesson. Hopefully you've read through the first page of notes that talks about differences in derivative notation as calculus has been developed, and the use of limits of difference quotients in order to find the derivative. And so we're going to break right here into example 1. We have a function y equals x squared plus 2x, and we want to find f prime of 3. So in order to find this derivative at this point, this represents, with the f prime notation, tells us we're finding the derivative at x equals 3. And so we're going to set up the limit of the difference quotient, the limit as h goes to 0, of f of 3 plus h minus f of 3 all over h. And there are other difference quotients that were highlighted on the front page that we could use to calculate this. This form of the difference quotient tends to be my go-to for when I'm finding derivatives, and so you'll see me use this one a lot. We could alternatively use pretty much any of the difference quotients in order to find this derivative, but this is my favorite, so it's the one I'm going to use. And now I'm going to substitute those values into the function in the numerator. And so I have 3 plus h, the quantity squared, plus 2 times the quantity 3 plus h, minus 3 squared, plus 2 times 3, all that over h. And then I'm going to expand all of this stuff out algebraically. That gives us 9 plus 6h plus h squared plus 6 plus 2h minus 9 minus 6 all over h. And these 9 and the minus 9 and the 6 and the minus 6 cancel each other out. Something you should be on the lookout for anytime you're finding a derivative using a difference quotient like this. Once you've made that cancellation step, everything in your numerator should contain an h. And that's kind of a check that you can use on your own work. If you've expanded things out and canceled things out, and there's something that doesn't contain an h in the numerator, you've made some kind of algebraic error, either in your setup or in your algebraic manipulation. And then now I can factor in the numerator. And now I can go ahead and cancel an h out of both of those. And we end up with the limit as h goes to 0 of quantity 8 plus h, which we'll find via substitution to be 8. And what does that mean? That means that the derivative of this function at 3 is equal to 8. And that represents the instantaneous rate of change at 3. That represents the slope of the tangent line at 3, or the value of the derivative at 3. Alright, let's go on, and we'll move on to example 2. In this case, we're going to do it for a general derivative. We can actually find general derivative formulas. Instead of finding the derivative at the point constantly, we can go ahead and use one of these limits of a difference quotient in order to find the actual formula, the function value for the derivative. And so we're going to go ahead and do that here, because in example 2 we're told to just find dy dx. So we're going to try and find a formula for the derivative. So instead of having a numerical value to substitute into our difference quotient, we're going to have the limit as h goes to 0 of f of x plus h minus f of x all over h. And now I'm going to go ahead and substitute those into the function. So I've got 2 times the quantity x plus h quantity squared minus 5 times the quantity x plus h minus, now here I'll just bring in my function as is. I've got all of that over h. Now I've got some algebra work to do. I've got to expand and simplify this numerator. So I've got 2 times the quantity x squared plus 2xh plus h squared minus 5 times the quantity x plus h minus the quantity 2x squared minus 5x all over h. And now in this step I'll handle distributing and getting rid of those constants. It's going to give me 2x squared plus 4xh plus 2h squared minus 5x minus 5h minus 2x squared plus 5x, all that over h. And you should be seeing a fairly similar pattern happen with these limits of difference quotients. You're going to have things that cancel out in the numerator. And once I've canceled those things out, everything else should contain an h. And so I've got the limit as h goes to 0 of 4xh plus 2h squared minus 5h all over h. I'm going to factor an h out in the numerator. Head up this way. And so the h in the numerator and denominator cancel each other out, and this turns into the limit as h goes to 0 of the quantity 4x plus 2h minus 5. Now I'm going to find this limit via substitution. I substitute 0 in for h, and all that's left is 4x minus 5. And so this is our derivative formula for the original function given here. And if you think about it, this is a pretty neat concept, where we now have a function that represents the instantaneous rate of change for any x value of the original function. So instead of finding the instantaneous rate of change at each individual point, if we find this function for the derivative, we can now use this to find that instantaneous rate of change at any point on the original function. It's kind of cool that when we have a formula for a function, we can come up with a similar formula that describes this characteristic of the function. I've always thought that that was kind of neat, kind of cool. Anyway, that's the end of this example, and that's going to be the end of this video. Join me next time for examples 3 and 4 in this lesson. See you then. Have a great day.